Hey guys, let's do this. We're going to be doing topic 1.3, elemental composition of pure substances. We're going to be going through and basically looking at what's the difference between a molecule and a formula unit, basically covalent and ionic bonds. And then we're going to be talking a lot about empirical formulas, how you can go about using these empirical formulas and something like a mass spectrometer to determine if something is pure or not, if it's actually a pure substance, and if it's not a pure substance. Okay, so let's do this. First off, what's the difference between an element and a compound? That's going to be our first step. One, an element is anything that contains one kind of atom. So just a helium atom by itself, that's going to be an element. An oxygen, diatomic molecule here, which is oxygen and oxygen, also an element. So an element is basically anything that has only one type of atom in it. For example, anytime I say the word elemental thing, like elemental oxygen or elemental helium or even elemental carbon, it's pure carbon, nothing else. Now, there's different, what are called allotropes. Different allotropes of some things, like elemental carbon could be graphite, which we find like in pencil lead, or it could also be a diamond. Those are both pure carbon, just different configurations of it. If it's an element, it is either by itself in the diatomic form or is in some other form, like carbon has a couple of different allotropes. Phosphorus also has a different type of some different allotropes there. So if we say it's a compound, it has two different types of atoms in it. So this is, as we can see, my favorite liquid, water. It has a hydrogen, and an oxygen bound together. That means it's a compound. It is not one type of atom. Next, the distinction we need to make here is what's the difference between a molecule and a formula unit. So a formula unit is really when you have an ionic bond. If you have two ions close together, they start to attract together and form an ionic bond. When this happens, usually it happens with not just two atoms together, but many atoms all coming together, and they typically form some sort of pattern called a crystal lattice. In the case of sodium chloride here, you can see it's just kind of a 1 1 1, like a sodium chloride pattern, and this is kind of a three-dimensional structure. This is one reason why sodium chloride is kind of cube shaped or rectangular shaped. Then you have covalently bonded molecules. So if it's a formula unit, it is ionically bonded. Molecules are covalently bonded. This is whenever you have multiple atoms, multiple types of atoms all together, forming some other structure, not a crystal lattice, but instead being bonded together. Molecules versus formula units, covalent versus ionic. Now, let's talk about what an empirical formula is. An empirical formula is just the proportion of atoms in a molecule or compound, a molecule or formula unit. The molecular formulas is the exact number of atoms in a molecule or compound. Really, what's the difference there? The difference is you can have something like the molecular formula was C6H12O6. This would be a molecular formula. There's going to be six in this molecule. There are six carbons, 12 hydrogens, and six oxygens. But if I were to go through and use something like a mass spectrometer, break all of these atoms apart and shoot them through and look at the abundances of each atom, then what I would get is a proportion. I would say, I could only really tell that there is one carbon for every two hydrogens and every one oxygen. Remember, what I did here was the cardinal sin. You don't necessarily need to write these ones, but I'm doing it just to show you. This would be your molecular formula, and this would be your empirical formula. Why do we even care about an empirical formula? Well, like I said, this is how, using something like a mass spectrometer, we can go through and actually determine how much of each element is in a certain compound. So in doing that, we can go through, determine what type of atom this actually is. Or what type of molecule this actually is. We can go through, and if we know the number of moles each thing is, we can go through and um, uh, determine its relative proportions. If we see that we have carbon at 0.166, oxygen at 0.166, and hydrogen at 0.333, we can determine what proportion these guys are. This may be a bit simplistic, but let me tell you kind of the process of this. What we need to do here is figure out the lowest number of moles, in this case 0.166. And then we take that number and we divide everything by that number. So for example, here it was 0.166. We're going to divide this by 0.166. And anything divided by itself is, of course, 1. 0.166 divided by itself is going to be 1. And here, 0.33 divided by 0.166 is going to be 2, roughly 2. So from this, we can now go through and we know that it's going to be 2 hydrogens for every 1 oxygen and 1 carbon. That is what we said before. This is going to be the empirical formula. This is nice, but we don't know if it's going to be CH2O or it could be C2H4O2. Or it could be any multiple of these things, but we're one step closer to discovering that actual molecular formula. So sometimes they don't necessarily give you grams or moles or anything like that. They give you percents, they give you relative abundances. You've seen this before with mass spec, where they give you a relative abundance of each thing. Now, if they do give you percents, what you can do is assume that you have a 100-gram total sample, and that turns each of these percents into grams. From there, you can take your grams and move it to moles, and then do what we did before, where we take the lowest number of moles, divide everything by that number, and that'll give us a proportion of elements, proportion of carbon, oxygen, and hydrogen. So that's the way we're going to go about finding an empirical formula. From then on, the next thing you can do, using these numbers, we can go through and just take these and turn them into grams. From there, we can then convert these over to moles. If we have 40 grams of carbon, let's do this up here. So 40 grams of carbon, and we know that the grams per mole of carbon is 12 grams per 1 mole. If you don't know that, you can always go through, look at your periodic table, and find carbon and see what its molecular weight is. From there, you can go through 40 divided by 12. So 40 divided by 12 is going to equal 3.33 moles. So we have that. Then you can go through and do the same thing for oxygen and for hydrogen. I've already done this one, so I'm just going to let you know it's going to be 3.33, 3.33, and 6.66. So this is going to be the number of moles. From there, you're going to do the exact same thing we did before, where we take the lowest number of moles, in this case 3.33, and then so that makes this 1, that makes this 1, and that makes this 2. So we're going to have 1 carbon for 1 oxygen for 2 hydrogens. So it's the same example that we've been working with. But how do you go now from this empirical formula? That's 2. So how do you go from this empirical formula to the molecular formula? So what we can do is figure out the molecular weight of this guy. So the molecular weight of this is going to be, so for carbon, it's 12. For hydrogen, it's 1, but there's 2 of them. And then oxygen is going to be 16. The molecular weight of this guy is 30. So the way we go from the empirical formula to the molecular formula, we need to know one more piece of information, and that is with the molecular weight of the substance. You can figure out the molecular weight of the substance through a couple of different ways, experimentally, but in a AP classroom environment, they're just going to let you know in the question. It's if it's 180. 30 is for this one. The molecular formula, it's 180. What we can do is take 30 divided by 180, and this is going to get us 6. So 180 is 6 times 30. So what we can do is, now that we have this number, we can multiply all of the subscripts down here by 6. We have C6, H12, and oxygen 6. So this is going to be how you go through and actually determine your empirical formula based on abundances. So again, let me review the steps for you. Step 1, take your abundances and turn them into grams by assuming a 100 gram sample. When you have grams, take your grams, convert them to moles. So once you have done the mole step, from there you take the smallest number of moles that you have and divide everything by that number. For that smallest number, you're going to get a 1. For your other numbers, you might get something a little bit different. But in this case, you have 1, 1, 2. So from there, you can go through and write out your empirical formula. Now, the empirical formula is going to get turned into the molecular formula if they've given you the molecular weight. That's going to be one more piece of information that they've need to give you. That's that for this video. I will see you guys later.